today with Clifford Burgess. So,
or maybe not.
Cliff is, by his own description, one hell of a guy. So, let's hope he will give us one hell of a talk.
Somebody hacked my website. And you look at the right screen there. There we go. All right. All right. So I know we're pressed for time. This is a talk heavy day. So I'll cut right to the chase. You'll notice that all my this is work done largely with Leo van Nierop, a student, and all my acknowledgements will be in this font that you can't read. So trust me, you've all been cited in the right places, and so it's, don't worry about that. So, and apologies also to a few of you have seen this talk, and there are some things at the end that might be a bit different, but my main message is there's good things coming from brain back reaction, and probably the biggest part of that message will come out in the first part of the talk. So the way I'd like to describe things to you is first I want to tell you the tool with which the conclusions are going to be drawn, and that is that the problem that Leo and I have solved is if you have a bunch of codimension or higher codimension sources, codimension being the number of dimensions transverse to the source, and you want to know, typically the kind of thing you want to know for cosmology or for particle physics is you choose some sources, like you choose their tensions or the properties, and you want to know what the implications are for the fields that they set up. Could be the size of the extra dimensions, could be the geometry on the branes of the sources, could be electromagnetic kind of fields. But you're interested in how to identify how the integration constants in the solutions depend on the physical properties of the sources. And I'm going to give you examples of that for codimension 2 sources. And the main message is that the systematic description of how to do this is very well known in codimension 1. Randall-Thunder models are full of descriptions of codimension 1 surfaces where there's one direction transverse to the surface, and things like the warp factor take specific jumps at the surface, and that jump is telling you how the geometry is responding to the branes. But there's very little known in a systematic way for higher codimension sources, and that's really unusual in particle physics and cosmology. So the main message of the talk is that you don't very often have virgin territory in our business, and this is largely virgin territory. There's some things that are known from string theory. Most of the people who think about this most are string theorists or people who worry about gravitational waves. But a systematic description in terms of arbitrary properties of sources is not on the table yet. And I'll tell you why that is when we get to that first part of the talk. Second part of the talk will be, and the third part will be implications of this particular applications for the specific case of codimension 2. So when I say higher codimension, it's going to be 2 for the talk. 2 is already different than 1, as you know from elementary mathematics. But it's different from 1 in the sense that the complications that arise for higher codimension already happen in codimension 2. But codimension 2 is special in the sense that in 2 dimensions, fields vary logarithmically typically, and it's hard for any one place of the space to get away from other places. And so there's going to be things that I'll tell you that will probably be specific to codimension 2. But in particular, one of the things will be there are known, we'd like to find cosmologies in higher dimensions, and ideally we'd like to find it by solving the higher dimensional field equations and not in some low energy approximation. That's well known to be hard, particularly for inflation. And in the inflationary case, it's hard, partly because it's hard to find de Sitter space, which is, if you're inflating, you're close to de Sitter space. If you can't find de Sitter space, it's hard to get close to it. And there are no-go theorems that have been inspired by that statement. And but one of the few counterexamples to that is there are some known de Sitter solutions to supergravities, and so the question is, why do they evade the no-go theorems? And I want to argue for you that the reason they evade the no-go theorems is because of back reaction, that the back reaction of the branes makes the solutions have properties that are assumed not to be there in the no-go theorems. And so that's probably got generalizations to higher dimensions than the one I'll show you, and that I'll just show you the criterion, but I won't give you solutions in those cases. The last part will be aiming at naturalness questions. And so I want to argue that for codimension 2, I'll essentially walk you through a calculation which is like the Goldberger-Wise calculation in Randall-Sunder models, where you watch the interactions between sources and the bulk stabilize moduli. And so there will be flat directions which will be lifted by the interactions with the branes. And that's useful because that dictates how big the extra dimensions are. And in many cases, that controls the hierarchy problem. And it tells you what the, if you know what the potential is for those flat directions, in particular, you know where things are stabilized and you know the value of the energy at the minimum, that tells you what the curvatures are and the cosmologic constants are. And the main message here will be, I want to show you that the parametric dependence on things is different than you would have been expecting if you didn't do back reaction or you only did codimension 1 back reaction. So that's the talk in the outline. So first part is the tools on which everything else is based. So first, there are a couple slides which I think are really not really necessary for this audience about extra dimensions and naturalness. And mainly I want to emphasize here that back reaction is an important part of the way we think about naturalness in extra dimensions. But one of the ways in which extra dimensions helps, you're worried typically about scalars in 4 dimensions, why there are properties that we like so much in cosmology, like they're being very light or their spaces not being very curved, seems to not be respected by loops. Loops like this are often the dangerous ones, and the problem is heavy guys in the loop give you large contributions, ultraviolet sensitive contributions to things that you like to be small. One way in which extra dimensions helps is that a scalar in 4 dimensions needn't be a scalar in higher dimensions, and so it can be protected by symmetries that weren't there in 4 dimensions. Second way in which it helps, I probably overshot there. Second way in which it helps is the observation that you can lower the quantum gravity scale. The way particle physicists argues that this thing depends on scales is you have, supposing you had gravitational couplings here so that each vertex gave you 1 over m Planck, then on dimensional grounds the change in the mass would depend on the biggest scale in the loop. That would be lambda. And a particle physicist would say, well, the biggest scale we can have is Planck scale, so that this whole thing is the Planck scale, so everything's large. But if you've got a theory where you've made the gravitational scale small compared to the Planck scale, the 4-dimensional Planck scale, then this now becomes a suppression of lambda over m. And that's something which is not what you would generically bargain for, but it's there. And that's, in large volume models, the inverse powers of volume that are often suppressing things in a surprising way essentially are coming to you in that way, that the things are saturating. String theory is doing good things for you, say, at scales that are small compared to the Planck scale. And you see that in the suppression between the string scale, say, and the Planck scale, which is powers of 1 over the volume. The last way, which is the one that I want to build on, is the back reaction statement. So the first 2 things you didn't need to have back reaction to talk about, but back reaction Randall-Sunder models tell us, among other things, that back reaction can change the way you think about the low energy theory in an important way. It makes things local. What's low energy in 4 dimensions can be local in the extra dimensions, is the observation. And the warping is important for that. And the thing I said already is that the response of the warping to the back reaction is something which is systematically worked out in codimension 1, but not so systematically elsewhere. And it's very rare that 1 dimension is representative of what goes on in higher than 1 dimension. So you expect different things to happen for higher codimensions. So why is it not worked out? The basic problem is, in Randall-Sunder models, if you want to know how the brane tension shows up in something, you just evaluate the action at the solution and everything's fine. You can do that, and there's no particular complications in relating integration constants to the brane properties. But in codimension 2 and higher, the basic problem is that fields start to diverge at the position of the sources. So things vary logarithmically in codimension 2, like 1 over r in codimension 3. Coulomb solution is the classic example, that the Coulomb field blows up at the position of the nucleus. And so that means that the matching between the properties of the field and the properties of the source is more subtle, because it's something which is a local property near the source. And it's not a framework in which effective field theory is normally cast, but it's a matching problem which can be solved, and I want to give you the solution in codimension 2. And the logic that I'm going to give you would apply to any codimension. I'm just going to give you it's simpler in codimension 2. So that's the problem, is that the basic problem is that fields are diverging at the sources. And so you think about how you dealt with that. The Coulomb solution is the thing to think about, because you were doing that on your mother's knee. You didn't worry about the fact that the sources were places where the fields were singular. And if you think about how you did that, in the end of the day, when you thought about electromagnetic solutions, you think about the the properties of the sources in a way which is not referring to the fields evaluated at the sources. You instead match onto the near field behavior, near source behavior of the fields. You match that onto the far field behavior of the fields. And so explicitly, if you think of what you really do, in electromagnetism, you think of some Gaussian pillbox around your source, and you never actually worry about the field dependence inside the pillbox. All you care about is what the boundary data was on that source, and in particular the flux through the sphere. And a more formal way of saying that is this, that if you're interested in fields that are varying over distances that are long compared to the size of your source, then there will exist some surface like a sphere which is midway in between. So it's far from the source, but not very far compared to the interests of the area distances of interest to you. And so one way to think about what you did when you did this Gaussian pillbox thing, but which would include higher multipoles, say, would be that you can think about, from the point of view of inside the sphere, you can think of figuring out what the fields are on the sphere as a far field problem, because the sphere is a long ways away from the size of the source. And so you can do a multipole expansion, and that'll be an expansion in ratios of the size of the size of the source, say it's the nucleus, divided by the size of the sphere, and it'll be under control. And the different multipoles will be encoded in a different angular dependence around the sphere. And then from the point of view of the outside of the sphere, you could say that, well, now I've got some boundary data, and I can pull off the various multipoles by looking at the angular dependence. And I'm mostly going to focus on the monopole part of it. And what you're effectively doing in the multipole expansion is you're pulling off coefficients of successive powers of 1 over r, which are far field from the point of view of the interior, but from the point of view of the exterior, that's a near source limit. And so one way to phrase what's going on here is that if you take a field like the electrostatic potential, and you take, if you're interested in the monopole part of it, you take r squared in 3 dimensions times ddr, and that would pick off the coefficient of 1 over r in the potential. And that's being related to the derivative of the action of that point particle with respect to the field. So if you thought of a point particle as being described by an action which is an integral of, charge times a along some world line, you differentiate with respect to a, and you're picking off the charge density essentially. And that's so this correspondence it's a matching between the integration constant, which is in this 1 over r term, and the physical properties of the brane, which are coming from, or the source, which are coming from differentiating with respect to the fields. So what I'm going to describe for you is the result of doing this for gravity too. So it's going to be this logic literally, and I'll be more specific in a second about exactly where it comes from. But what I'm going to give you, a solution to the problem of the matching between sources and fields, is a statement of the boundary conditions near the branes, or the sources, of various derivatives, and in 2 dimensions this will be r ddr basically, of the various fields, and they'll be related to derivatives of the functional derivatives of the source action with respect to those fields. So for example, for this problem, this is where I'll show you an explicit statement of what the boundary conditions are. So if you take scalar tensor theory basically, with codimension 2 sources described here, and take the geometry near the source to be rotationally invariant. So that's going to be like the monopole limit. It doesn't mean the whole geometry is rotationally invariant. It just means the near field geometry is rotationally invariant. So it has this kind of a thing. It's described by a warp factor. I'm going to take things to be maximally symmetric on the brane, but you can generalize that to be time dependent if you like. And there's a piece of the metric over here which is also got to be described, and there's also the scalar field. You're looking for 3 boundary conditions basically. The derivatives of these 3 functions as you are near the source. And this is what it turns out to be, and I'll tell you how I drive it in a second. So here are the 3 fields, and then primes are the radial derivatives, and e to the b was basically the radius, remember, in the metric. So this is like r ddr. So that's the left-hand side is radial derivatives as you're expecting, and the right-hand side is derivatives of the brane action with respect to those fields. Now, one thing that might surprise you here is that one of the derivatives is with respect to the theta part of the metric, which is not, you don't normally think of the action in codimension 2 being a function of the theta part of the metric. You normally would have thought it's you would have taken the action to be something like, integral of root g of the degrees of freedom on the metric, say, and maybe plus higher derivative terms, maybe with a tension. And so you might think this is not so useful because you'd have to know a dependence that you're not normally interested in. But you don't actually never need to figure out that derivative, because everybody on the right-hand side is subject to a constraint, and the constraint comes from the left-hand side, and it comes from the left-hand side. It's really an expression of the Hamiltonian constraint. If you imagine integrating the field equations out from the brane in the radial direction, then you know that the initial data, the first derivatives as a function of r, those are not independent, and there's a quadratic relationship amongst them which has to be enforced, and that relationship enforces a bunch of relationships amongst these derivatives, and this is what it turns out to be. And so the thing that you can calculate easily is the derivative of the Lagrangian with respect to phi or with respect to the on-brane metric. And this expression tells you how to solve the one you don't have in terms of the ones you do have. So it's, in practice, you don't need to know what the dependence was on theta theta. Later on, it's going to be useful to know that U vanishes in the case that the Lagrangian does not depend on scalar fields. That's something which will play a role later on. Okay, so how do you, before I tell you how I got those formulas, let me tell you two properties that are important about them. So the first thing is that I didn't emphasize it, but both sides of that equation could have diverged. We're looking at fields. They had to be evaluated at the position of the brane, and so the fields can be diverging. And the brane action is being evaluated at the position of the brane, which is also diverging. And so you can regularize that by not going quite to the brane in various ways. And the important thing is that, the divergences that you get in that way can be renormalized, and they're renormalized into renormalizations of the brane couplings. So it's the usual story for renormalization. It's a surprise, perhaps, that you see it at tree level rather than at loop level, but it's something which is just generically true, that the bulk fields, the divergences of bulk fields near the brane can be interpreted as renormalization of brane couplings. That's an observation that had been made by Goldberg and Wise and others earlier in a more restricted situation, but it's true in general. The second thing is those matching conditions I gave you. I'm kind of delaying telling you how I derived them, because I want to emphasize before telling you that these matching conditions are very robust. So the way I'm going to derive them is going to be a very concrete way. I'm going to regularize the divergences near the brane in a specific way that I'll tell you about in a second. I'm going to essentially excise the position of the source and then with some sort of a cylinder and then replace the interior by some smooth geometry. And then I can use just regular Israel junction conditions across the codimension 1 boundary of that division. But the important thing is that the answer you get is robust, and there's and I'm going to give you two lines of argument that show you why. One of them is the physical one. If you think of the Coulomb problem, if I had some nucleus or something and I'm interested in the monopole behavior, I can describe that with any old charge distribution that has the same charge. It doesn't matter what it is. It's any kludgy combination of things which has the right charge compared to the physical source of interest for the monopoles, the multipole moments of interest, will give you the right answer. That's essentially the physical argument what's going on. The check will be, I'm going to take these rules I've given you and apply them to a case which is not one for which you would have thought that my construction will apply in coming from string theory, and you'll see that they work. So the way I actually derived those rules, or the way that Leo and I derived those rules, was to take your codimension 1 object and excise it by some cylinder. You put some action on the cylinder, you put some smooth geometry in the middle here, and then you have ordinary junction conditions across the cylinder which relate derivatives on the outside to derivatives on the inside. And then the smoothness in the middle gives you a boundary condition in the middle. And then you dimensionally reduce the whole thing to make it small. And in that limit, you ask what it looks like. And that gives you the boundary conditions, the junction conditions that I had that you would get in that way, dimensionally reduced to the quantities I showed you on the previous slides. Now, the check that this is not crazy, besides the physical argument that I gave you that it shouldn't depend on anything. This construction is not important in those boundary conditions. It's really, all that's being captured here is the lowest multiple moments. A check on that is you can apply it to a situation where you know everything. So if you take D7s in type 2b supergravity in 10 dimensions, those are codimension 2 sources, or PQ branes. It doesn't have to be D7s, or orientifolds for that matter. And what you can do in that case is you know a whole bunch of solutions, the stringy cosmic string solutions for which the metric and the axiodilaton are varying. And so you know what they do, you know how they approach the sources, and so you know what the left-hand side of my conditions were. The right-hand side you also know because you know the actions of these things, and so you can differentiate them on the right-hand side and you ask what they do. And they do a nice thing, it turns out. In that particular case, for D branes coupled to the axiodilaton, it turns out that because of the target space metric that the axiodilaton has, and because of the D brane action, the functional form as you approach the brane is actually the same for both of them, so there's no singularity problems, which is kind of also nice if you're thinking of them as fundamental objects. And all those conditions I gave you degenerate down to a numerical condition that some coefficient on the left is equal to coefficient on the right. And what it does is it relates the Newton's constant in 10 dimensions to the tension of the brane. And it says, it's essentially the statement that the tension of the brane can be calculated in terms of alpha prime. And there's a numerical factor which turns out to be 2. And if you compare to Polchinski, it's the right factor of 2. So if you weren't convinced by the physical argument, that's a reality check that even though this is a very kludgy construction, applied to this particular instance, it captures what's going on properly. And so So the message there is that the conclusions I'm going to draw for you are robust and don't depend on the details of this particular way of deriving the matching conditions. So that's the end of the heavy lifting part of the talk. So what I'm going to do now is take the derivatives, those matching conditions, and apply them in various situations. And the two cases I'm going to focus on are finding de Sitter solutions and looking at flat solutions or cases where you stabilize moduli. Let me start with the Sitter solutions. So I want to argue that these boundary conditions are essentially singular. They're telling you, often you're told that codimension 2 options or objects have things, they're conical singularities, like a cosmic string would be. But that can be true, but it needn't be true. Generically, if you couple a cosmic string to a field, a scalar field, say, the field will get a logarithmic dependence. Its gradients will go like 1 over r. Those things will be stress energy, and curvature will see that. So the generic situation is you have curvature singularities where you have sources. And in all cases, this description I'm giving you will cover it. But those singularities are important because in some of the no-go theorems for de Sitter space, in particular the Wesley-Steinhardt one, they make a very benign sounding assumption about compactness of the extra dimensions, which is not being satisfied by the presence of the fields near the sources. The fact that they're diverging the way they are, what you want to do is excise the sources with little boundaries, and then you're getting boundary contributions essentially where that the no-go theorems would be assuming would be 0, but which are really being dictated by the properties of the sources. Okay, so what you like to do, the motivation here is, again, you'd like to have cosmologies and extra dimensions, honest-to-God ones. I'm going to skip over a part of the talk which describes one. It's one of the first inflationary solutions, which is explicitly a solution of the higher dimensional equations based on a 6-dimensional de Sitter solution that's known. But I'll skip that actually when I get to it. And this warm-up will just really tell you why the no-go thing doesn't get in the way. So it's hard to get de Sitter space. That's why it's been hard to get inflation. And so that's spawned the no-go results. And the ones I'm going to focus on are mostly the Wesley and Steinhardt ones. And so I want to describe how the argument would go through, keeping track now of what the near brane behavior of the fields is. So the way the argument typically goes is you've got an action, you've got the Einstein piece, and then all the rest of the stuff in your supergravity, and you've got these sources. And you look at an action at a configuration like this, where you've got some warped geometry and some extra dimensional geometry whose details aren't really going to be very important to what I say. If you look at the Einstein equations in the on brane directions, the ones parallel to the sources, and take their trace, you can write it in this particular way. You can write it as being a term involving the scalar curvature for this induced metric, for this metric on the source, which I'm going to assume is maximally symmetric. So this is either de Sitter space, anti-de Sitter space, or flat for the purposes of what I'm going to do. But you can generalize it beyond that if you want. And this thing, the integral of this thing over the extra dimensions, is equal to 4 terms actually. There's one I'm not writing here, but I'll tell you why in a second. There's a term which is essentially taking this action and evaluating it at the solution of the that you've just found of the equations of motion. There's a piece which comes from trading the scalar curvature in the extra dimensions for the induced one, which involves derivatives of the warp factor, which is the total derivative. And then there's a piece involving the derivative of the source action. And then the piece I didn't write was the one involving the matter action here. And that's typically, the reason I didn't write it would be contributing if you had space-filling fluxes, say. But generally, maximal symmetry in the absence of space-filling fluxes in supergravity will make this last term be 0, and so that's why I'm not writing it. But if in a particular application you want to check that it's 0. So now the way that the no-go theorems often work is you take these things and you recognize that this term often vanishes. This is one which has a very definite sign because basically del squared has a definite sign. And then often this one is ignored because you're looking at the solutions in the bulk away from the sources, and so you think that those things should be vanishing there. And so what really goes on, the thing I'm going to say now is going to kind of seem pretty obvious, because these are the things that I've said derivatives of the action with respect to the fields should be related to asymptotic near brane behavior of fields as you approach those surfaces. And here's something which is an integral of a total derivative, which if you had thought the space was compact, you would have said was 0. But if you really have sources, and those sources, the configurations of the fields are singular there, what we'll do is we'll excise the sources with these little, so here's the source. We'll just take a little area around it. And then when we do this integral over the extra dimensions, we'll have to pick up all the normal derivatives that are appearing on these boundaries. And those are the things that are explicitly going to come to you as radial derivatives, which are the things that are being related by the matching conditions to things like this. And so the interesting thing that happens is that this particular thing that you get is exactly minus this thing, because the particular derivative that's appearing here is exactly the derivative that the matching conditions would tell you you would find are related to the radial derivative that you're getting of w here when you evaluate all the boundary terms. So regardless of what the sources are, those two terms are canceling for codimension 2 sources generically. And so all you're really left with, even though this one has a definite sign, you don't really care because it's being cancelled by something else which also has a definite sign and is the opposite. And so the answer is really being controlled by this term, which is the one that often vanishes but needn't vanish. And so the question is, what's its sign, or what's it controlled by? Now the good news there is that for supergravities, almost all higher dimensional supergravities have scale invariances where you multiply the metric by a constant and shift the dilaton, say, and then the whole action scales by a factor. So that's the symmetry of the classical equations of motion. Whenever you have that, this on-shell action is always the integral of a total derivative, because that's a consequence of scale invariance. So there's always something for which this thing is the d of something. And so that means that the bad news is that you needed to know the solutions, and you needed to know the back reaction in order to decide what the sign of the curvature is. The good news is you didn't need to know most of the details of the solutions. All you need to know is the near brane boundary conditions of a specific combination of fields, which are the ones whose derivative give you the on-shell action. So in the 6-dimensional de Sitter example, the reason that you get de Sitter space is that this has a positive sign. This is the one that gives you the de Sitter sign. And that's controlled by in that case, it's you'll see in a second, it's the dilaton radial derivative as you approach the branes, because in that particular supergravity, the total derivative is del squared of the dilaton. And so all you need to do is design a dilaton which has a derivative of its action which is positive, and then that'll give you a de Sitter-like solution, and that's why those solutions exist. In the higher dimensions, in 10 dimensions, we can tell you what these omegas are. This is now a collaboration not just with Leo, this is now with many people in the room here, like Fernando and Hamid. And so there's an expression for what the, and Anshuman, Maharana, expression for what these omegas are for various 10-dimensional higher 10-dimensional supergravities. The thing that we can't tell you yet is there a real honest-to-God source which has the right derivatives for those things to give you de Sitter space? But the tool clearly is to use these things, because all the information you need for an exact statement at the classical level is the boundary behavior of this quantity omega for the supergravity that you like, and then the matching conditions will tie that to properties of the source that's supporting that's sourcing the configuration you're looking at, and then you want to find, is there a physically reasonable source for which you can get de Sitter space? The existence proof is that in 6 dimensions there is one, and so it's very plausible to me that there should be one in 10 dimensions too. And this I told you before. It's just the good news is that you don't need to know the whole solution. It's just the asymptotic forms that are important. Now at this point, I would have told you about an explicit solution that you can, you're not surprised if I give you de Sitter space in 6 dimensions and I can find inflation in 6 dimensions, because I'll be near de Sitter space and I'll roll towards it. And there's a story there which has a nice feature that because you solve all the equations in the extra dimensions, you can see what the extra dimensions are doing, and they actually are growing. While the extra dimensions, the 4 dimensions that you're inflating are blowing out almost exponentially, the 2 dimensions that you're not inflating are very robustly expanding like a power law. And so there's a definite evolution of physical properties during inflation, which is kind of cool to follow. But I'm going to kind of skip this. So I'm going to cut to the chase here. But if you, I can threaten you with slides there if you're interested. Sorry. That's supposed to be that link that I can, there we go. All right, so the missing slides, which will actually be on the web if you want to look at them, describe the near de Sitter solutions, which are slow rolls, and how you make matter coupled to them in such a way that you can have the slow roll end. Okay, so that's the end of the de Sitter story. The last part of the talk is naturalness issues, and those naturalness issues are going to be all about using the interactions between the brane and the sources to lift flat directions. And the questions you want to ask are, how big are the extra dimensions when you've done that? And how curved are the branes when you finish that? And what choices can you make for the branes which give you things you want, like very uncurved branes or very large dimensions, let's say. And you're looking for things that are technically natural when you do this. So you'd like to have things where you're not sticking in small numbers, and what you do is stable under doing loops. And one thing, the main thing you'll see here is that I've given you actually a very general statement as to what the curvature, when the curvature should be 0, because the same argument I gave you for de Sitter space will apply for flat space. And I'm going to take you through an apparent contradiction between that general statement and an explicit, no branes, just take a simple linearized calculation around a simple solution, and it's going to, at face value, look like they give you different answers, and I'm going to resolve that paradox for you in this section. But the main message is I want to focus on the moduli in these extra-dimensional solutions, and I'm going to focus on a particular one because it's going to be a six-dimensional example for which there's only one modulus, and I'm going to be interested in asking how the interactions between the branes and the bulk lift this flat direction. And what's going on behind the board is going to, physically what's going on is that if you had a constant field, let's say, which was a flat direction, but you choose your sources so that they depend on that field, then they have to have non-zero derivatives. The field has to have non-zero derivatives at the branes, and so that can remove the freedom to have a flat solution. That'll be where your zero mode went, and that's why you've lifted the flat direction. But my goal will be to give you a formula for the potential, essentially, how the flat direction, what it turned into. So it's no longer flat. What's its shape? Where is it minimized? And what's the value of the potential at its minimum? And I want to argue for you that at the very end there, that this will be another way of getting exponentially large dimensions. It'll be different from the large volume way, but it's similar in spirit to it. And then I want to focus also on what controls the curvature on the brane in these kind of models, and in particular ask what makes it flat, because we want to know the cosmological constant problem in this context is you ask what conditions give you flat on brane properties, and then are those conditions stable under doing loops? And so the first thing you have to do is know what the conditions are, and so that's what this will tell you. Okay, so I'm going to focus on a six-dimensional supergravity and then also a non-supersymmetric example to contrast them. And in that case, the argument I gave you a couple slides ago says that the curvature on the branes, the curvature scalar, is just controlled by the on-shell action in the same way that I argued before. And in this particular case, what's going to happen is that the total derivative the on-shell action is given by is del squared of the dilaton, which will be a scalar field sitting in the bulk. And so that, by the matching conditions, if I integrate this using Gauss's theorem and trade it for a normal derivative near the branes, then that radial derivative that you get here will be proportional to the derivative of the source action with respect to the dilaton. And so right without doing anything, the claim I would make is that if you want something flat, the thing you need to do, a sufficient condition for having a flat geometry would be to have branes that do not couple to the dilaton. And that's going to transpire to be true at the end of the day, but I'm going to show you that there's a paradox in that statement. It's a very seductive statement because absence of a coupling between branes and the bulk is something which is stable like crazy under loops on the brane. It needn't be stable against loops in the bulk, but it certainly is stable. If you don't have any couplings between phi and brane particles, you can do as many brane loops as you like, you're not going to grow one. You have to do a bulk loop somewhere to get a phi dependence and ruin this condition that this thing vanishes. So it's very attractive from the point of view of the cosmological constant problem. Right, so what about the paradox? I want to give you here's the model. So I'm going to take you through just a really donkey-headed calculation of how the system responds to changes of tension. And I want to contrast it to this general statement that I just described, that the curvature is always controlled by, it should vanish whenever the tension doesn't depend on the dilaton. So I'm going to take a case where it does not depend on the dilaton, and I'm going to do a calculation which seems to say that you get a curvature if you change the tensions in a way which is still independent of the dilaton, and then I'll resolve why that naive calculation doesn't contradict this statement. So here's where I want to do the donkey-headed calculation. It's a scalar tensor theory in 6 dimensions again, and there's a Maxwell field which is going to be a flux that will stabilize the 6 dimensions, which you have to do if you want to understand the geometry of the branes. And the two cases I want to contrast are the supersymmetric case and a non-supersymmetric case, and I want them both to have a flat direction. So the way I'll do that is, for the non-supersymmetric case, this parameter A will be 0, so that the scalar field doesn't couple to the Maxwell field, and the potential will be a constant. It'll just be a cosmological constant in the bulk. And in that case, there's a shift symmetry, and that's what makes this phi give you a flat direction. In the supersymmetric case, for Nishino-Sezgin supergravity, A will be 1, and so there is so e to the phi is playing a role, a gauge coupling basically, and there will be a potential energy for the dilaton, which is given by constants involved, the Newton's constant, and also a particular gauge coupling constant in 6 dimensions, but it's exponential in phi. In that case, it's less obvious, but there's still a flat direction, and there's a flat direction because this action has a scale symmetry of the type I alluded to before, where the metric shifts, or you multiply the metric by a constant factor, you shift the dilaton by a constant, and there's a combination which is always scales the action in the same way. So both cases, it's a flat direction. The question is, what happens to it when you perturb things like the tension of the branes? So where are the branes? I'm going to take the simplest solution of this thing, which is this rugby ball solution, where you have I'm going to give you a solution of the equations which has got the topology of a sphere, and it's got the metric of a sphere too. And we'll remove a wedge along 2 lines of longitude, glue the edges together, and then the conical singularities at the north and south pole will be the gravitational response of the tension of 2 branes. There are more general solutions known where the tensions are different and the geometries can be warped, but I want to focus on this one because it's very easy to describe and you can see what's going on and what the obstruction is that I'm trying to allude to. So the solution has a spherical extra dimension. Alpha not being 1 is encoding the conical singularity. L is essentially morally the size of the extra dimensions. It'll be maximally symmetric in the 4 dimensions that we're not drawing on that picture. But it's not flat necessarily. It could be de Sitter space or anti-de Sitter space. The Maxwell field has some normalization Q, and the scalar field is a constant. And that's a solution to the field equations for both those systems I described on the previous slide. All right, so the notable features are the magnetic flux, which is stabilizing the extra dimensions, is important. And so when we talk about flux quantization, you're going to find that it's going to play a role in fixing what the constant Q is. The second thing that's important is that there's a flat direction, and in both cases it's described by the value of phi. And so nothing in the field equation should tell you what phi naught is. And the third thing I want you to see, to keep track of, is that in the supersymmetric case, when A is not 0, this whole size of this metric is going like an exponential in phi. So that when you stabilize phi, in the supersymmetric case, you're also stabilizing the extra dimensional radius. But it's naturally exponentially large in phi. So if you stabilize phi at some moderately big value, then the radius is going to want to be exponentially big. Okay, so now here's the solution. What about the back reaction? Those conditions I gave you in the case of a conical singularity degenerate down to something very simple. They degenerate down to something that people have known since the early 80s. I think Vilenkin derived it first. It relates the defect angle in the cone to the tension of the source. And so that's the back reaction. So now there's a total of 5 parameters here. There's alpha, which is essentially the tension of the sources. There's phi naught. There's L. There's Q. And there's a curvature scalar for the extra dimensions. So those 5 things. We're not expecting phi naught to ever be fixed because there's a symmetry in the problem. So there should be formulas that relate the other ones. And what I want to do is take the field equations and show you that they relate 3 of these quantities, which I'll take to be Q, L, and the curvature in the extra dimension and on the branes, and I can write them, solve them as a function of alpha, so that the thing that you get to specify is the tension of the branes. So here's how you do that. The field equations, there's 2 of them basically, one for each curvature in the extra dimensions and on brane directions, and then there's also a flux quantization condition for the Maxwell flux on the sphere. And so there's 3 equations here. We solve them for Q, L, and R hat. And we get formulas for all those things as a function of alpha. No surprises there. And what we'll do now is we'll tune lambda to make the curvature. Now I'm focusing on the non-supersymmetric case. So I'm going to take A equals 1. And these solutions I gave you were the ones for A equals 0, sorry. And so in this case, there's no surprise why phi naught didn't appear anywhere, because it was an axion. And what I'll do is I have lambda as a cosmological constant in the extra dimensions, and so I'll tune it to make the on-brane geometry flat, and then we'll perturb the tensions, and that'll be a change in alpha, and we can just ask, what does everybody do? So how does the size of the extra dimensions change? How does the curvature change? And we're not going to retune lambda, so we're going to get some curvature, and the question is, how big is it? And here's what you find, is that you tune things in this way, and if you change the tension by some small amount delta t, and I linearize all those equations I showed you in the previous slide, you find the curvature turns into something non-zero, and it's something which is rho times a bunch of numbers, and the numbers are chosen because that's essentially the Einstein, the 4-dimensional Newton constant. And so rho, written this way, is the thing that you would have interpreted in 4 dimensions as being your cosmological constant that would be responsible for getting that curvature, and rho turns out to be twice delta t, and that's exactly what you expected because you changed the tension by delta t at both ends by the same amount to keep this to make the thing not warp. You wanted to stay a sphere. And so this shows you that extra dimensions in themselves are no miracle. And so this is the reality check that says that there's nothing crazy going on here. In 4 dimensions, there's no surprises, and I want to focus on the supersymmetric case, which is very different. The argument will be that the supersymmetric case gives you a parametric suppression compared to this. And the reason for it is kind of partly coming from the fact that if you ask where does energy come from, when you linearize all the equations, it's coming from, physically what's going on is that you change the tension, you change the defect angle, so you change the volume, but the flux is trying to satisfy flux quantization conditions, so it has to adjust to compensate for the change in volume. And it's the energy in that flux change which is the thing that turns out to be the thing that gives you the curvature. Everything else cancels out. And so it's expensive because that flux change was homogeneous in the extra dimensions, so it was proportional to the volume. And I'm going to show you that in the supersymmetric case, you get something which is less expensive. It's something which is not proportional to that volume. And so things will all be down compared to factors of the volume compared to what you're getting here. All right, so let's do the same thing for SUSY. So now for the SUSY case, here's our solution again. We have one more equation because we have the dilaton equation is non-trivial now. It's no longer an axion. It couples to the Maxwell field. So we have these three equations now. The two of them are Einstein equations, and one of them is a dilaton equation. And we still have flux quantization. Again, you solve for everything. And the interesting thing here is that Q, the thing that tells you how big the flux is no longer an integration constant. It's dictated to you in terms of numbers in your Lagrangian. So if you change the volume in the way that I was describing before, when you change the tension, the flux can't adjust because the field strength is nailed down to a number. And that leads to a paradox, which you can kind of see over here. Flux quantization is directly proportional to alpha. If you try and change alpha by changing the tension, you've got a direct obstruction in the flux quantization condition. And what that really means is that the solution won't be maximally symmetric. There'll be some time-dependent solution, and that's so the interpretation was that that's something which is giving you a big answer. But whatever it is, it's not consistent with what I told you before at face value, that if I change the tension in a phi-independent way, I should not be getting a curvature if it was maximally symmetric. So what's going on there? Right, so I want to resolve this paradox. And the resolution is that this calculation I just showed you is not being consistent in the number of derivatives it keeps. So we've worked to the 2-derivative level in the bulk, but we worked to the 0-derivative level on the brane. And at the derivative, what's happening is that tension is trying to drop out of the answer for the curvature. And so the subdominant term in the derivative expansion on the brane is the dominant thing. And if you have to follow it to see what's going on. And so what is that? You might have thought that the next term in a derivative expansion would have 2 derivatives, because that's normally what happens is that the kinetic terms. But it turns out that for these systems, because of the Maxwell field, there's a 1-derivative term you can write. In the brane action can start with a tension, which could have depended on phi. But it could also have something which is linear in the Maxwell field, because I take the dual of that in 6 dimensions, that's a 4 form, I can integrate that on the surface of a brane. If I had been talking about cosmic strings in 4 dimensions, the same thing would have happened. In 4 dimensions, the dual of a Maxwell field would have been a 2 form again, and then I can integrate that on the surface of a cosmic string. And if I had done that, then this would have had the interpretation of being the magnetic flux that was in that cosmic string. So it's something which is a standard thing when you see it for cosmic strings, and it's just a slightly different context for it here. To show you that the same interpretation applies here, that this is describing, phi is describing magnetic flux on the brane, what we have to do is just re-ask the quantization condition, what it becomes with that term. This changes the boundary condition for the electromagnetic field, and so it changes the flux quantization argument. And this is what it turns into, that the integer is equal to the integral of f, but now there's a new piece coming from the branes. And so now you can see where I'm going to go. The solution we had, f could not adjust for a change. If you change the volume by changing the tension, this changes because f can't adjust. And so the paradox was the left-hand side wasn't changing at all because it was an integer. But now we can make it work because this thing can adjust. But because it's localized in the brane, the energy cost of that is not scaling with the volume of the extra dimensions because it's localized. And so what I want to do is now linearize the field equations, keeping that, and I'm going to linearize more generally than the ones that are spheres. And then you can just solve everything. You can find out what all the integration constants are and ask how they all depend on the parameters, and just ask what's the answer, what's the potential look like, and what does the cosmologic constant look like. So we'll look at a more general class of solutions in this rugby ball, and we're going to linearize around the rugby ball, and we're going to ask, how does that phi change the argument I gave you? And I'm not going to give you the details unless you ask about it, because we're heading for a closing time at the end of 15 minutes. So let me just skip those few slides. And this is what the answer is. So what you do is you linearize the equations, you calculate directly what the curvature on the brane is, and then you say what potential in 4 dimensions would have given me that curvature as a function of the flat direction parameter phi. And this is the answer, it turns out. If you give me r hat, if you solve those equations for r hat as a function of phi, you plug it into this integral, and that gives you the potential that you would have interpreted in 4 dimensions as being the one responsible. And so what you're interested in practice is, where is this potential stabilized? So what's the derivative of that potential equals 0, say? Because that's going to be the value of the field, the flat direction field that is picked out by the stabilization mechanism. And then you also want to know what's the value of the potential at that point, and that's what these two formulas are. So I'm giving you here the non-supersymmetric case, and telling you the answer of this linearization story. And you shouldn't be surprised by what you're seeing here. This says that the condition for the value of phi is essentially you take the brane Lagrangian, which was a tension and it was a flux term, and this is the combination that corresponds to taking that thing and evaluating it at the combination I gave you. So this is essentially the brane Lagrangian. It depends on phi, or if it depends on phi, you're supposed to differentiate that with respect to phi, and then that condition for when that vanishes is what tells you what phi is, this flat direction field. That makes sense at some level, because why was there flat direction? It was because there was a shift symmetry. If these guys depend on phi, you've broken the shift symmetry, and so the thing that's giving you the information that picks the value of phi is the phi dependence of the brane Lagrangian. So this is what you would have thought in a probe approximation. If you just stick a brane Lagrangian on, you differentiate it, that's the thing that's giving you the potential. The one thing that's a little bit of a surprise is that the value of the potential at that point, at that minimum, is this. It's almost the brane Lagrangian, except for that factor of 2. If we only had tensions, which I had in the previous example, it would have been literally the brane tension, and that's why we got the tension there. But the flux actually counts twice. It comes once because it's the brane Lagrangian, but then also this adjustment of the volume to the perturbation is competitive with that. And so they're the same size, and there's an extra factor of 2 that comes from that, it turns out. But it's no big deal there. This is kind of verifying that the non-supersymmetric thing went through the way I told you it should have done. And phi didn't really change it by much. But in the SUSY case, it's an important difference. So the main thing is that if you look at where that formula stabilizes the flat direction, it's now given by a condition like this, which is not just derivatives of the brane action, it's also another factor involving the action itself. What's going on there is that the symmetry that was responsible for the flat direction was scale invariance now, so it sees the metric and not just the shift symmetry. So if you dimensionally reduce, if you like, when you dimensionally reduce, you're not in the 4-dimensional Einstein frame. If you went to the 4-dimensional Einstein frame, you would have had the thing that you would have gotten naively times some factor coming from this flat direction field. And that's the thing you'd want to minimize. And so the fact that you've got things involving no derivatives as well as things involving derivatives is kind of because you're looking at an Einstein frame potential that you're minimizing. So it's not so surprising, but that's what it turns out to be. And then the value of the potential at that minimum is exactly what it was before. It's exactly the same formula as before, but because this has changed, I can trade this for this. And that's something which involves derivatives of the tension, or the Lagrangian of the brane, which is what I told you the general answer was. And the factors of 2 work. So this says that you don't have to have a brane on which you can localize flux. And if you don't, then it will be true that you've got a very rigid system that can't respond to perturbations. But if you take a generic action, which has, in particular, keep the first subdominant term in the brane action, which is the brane localized flux, then what you find is that the system is no longer so rigid because you can stick a little bit of flux on the brane. And when you do that, the energy that you get when you lift the flat directions is exactly what the general argument told you had to get. And so, God is in his heaven and everything's consistent. But that means that the statement that the absence of a coupling to a scalar field is true, provided that you can localize flux on your brane. Okay, so I'm going to close this with 3 intriguing examples. So the first is the reality check example. If we take the scale invariant case, this is the Weinberg theorem case, Weinberg's no-go theorem case, we should get what we expect from scale invariance. Scale invariance should tell us that, if we naively you would have said if you couple the brane in a scale invariant way to the bulk, you don't lift the flat direction. But you can, and that's Weinberg's point, is that the scale invariance can't forbid you having an exponential potential. And so the scale invariance criterion in this case is that T is independent of phi. That's the thing that you have to have in order for the brane to scale the same way as the bulk does. But because the flux term has more metrics in it, it has to have a very specific phi dependence in order to be scale invariant. It has to go like e to the minus phi. And that's special because the flux quantization condition involved this times e to the phi, and so it's something which is flux independent. So if you go through the exercise I just told you, the potential you would have gotten is something which is an exponential in phi, and it has some coefficient involving the tensions, which may or may not be 0. And it's exactly what you would have expected from scale invariance, and just as Weinberg's theorem would have told you should have gotten. A second intriguing choice is, let's just say T depends on phi in some way. I don't know what it is, but it has a minimum somewhere. So we'll just say near the minimum it's got some quadratic expansion, and let's say that we take this parameter nu to be 50 or something like that. And then what you'll find typically when you stabilize when you find where the extra dimension stabilizes, or where the flat direction stabilizes, is that phi will be minus 50. But you remember that in the supersymmetric case, the radius was exponential in phi, and so that in that way you've actually generated an exponentially large volume. You remember what was wrong with the ADD solution to the hierarchy problem was that they didn't tell you why the extra dimensions were large. This is telling you why the extra dimensions can be large in a natural way.
So where does that expression come from for delta TB?
This is something which I'm just saying, I don't know what T is. If I just phenomenologically take a function of phi, which has a minimum, then I can expand near that minimum. And as long as the minimum is at some value of phi which is reasonably large, then that will stabilize phi at a large value. So I'm taking the point of view that these branes are some phenomenological object, and so it might be some complicated D7s wrapped around various cycles. And the point is that the microscopics aren't important for the macroscopic response. And so in the same way that you don't need to know what the Earth is made out of in terms of D-branes to figure out what its gravitational field is, you don't need to know what the details of this construction are, as long as you end up in 6 dimensions with some codimension 2 thing, which has a phi-dependent tension. then this would be what you'd get. Now the third intriguing choice is the one I started with, that if nothing depends on phi at all, then your answer as an exact classical statement is 0 for the on-brane curvatures. And that's spectacular because classically you're starting off with nothing, and that's really just expressing the fact that the first solutions that we looked at had the property that the curvatures were 0 even though the tension was arbitrary, and which is something which we're familiar with from cosmic strings. The cosmic string is flat no matter what the tension of the string is. And so this is just the extra dimensions expressing that classically. Of course, the question is loops, and what do loops do to this? And the good news is that that condition, so now that we know what a sufficient condition for flatness is, we can ask if it's stable under changing loops. And the good news is that the brane loops are not a problem at all. And that's where the dangerous stuff was. In a supersymmetric context, these branes would typically be not supersymmetric if you wanted to use them in the cosmological constant problem. So the guys that are dangerous, like the electron or the W boson, are on the brane. And this is telling you that as long as you never do a loop for which part of the loop is coming in the bulk, you're safe from those guys, because they, if they don't couple it with phi to start with, you can't get a coupling to phi doing only brane loops. So the dangerous things to follow are bulk loops, but the bulk knows about supersymmetry, and so there's some special magic that happens there. So I told you there'd be something new at the end of the talk for those who've seen it before, and this is where I stick the stick into the hornet's nest. And so we've actually calculated the bulk loops at the one loop size, at the one loop level, and they're all small. And there's actually a stupidly obvious reason for it in retrospect. They're small because generically what happens is that the bulk renormalizes things. But if you look at that brane action, the bulk action, the supergravity action, the reason it was scale invariant was that there existed a string frame where you could write e to the minus 2 phi in front of everything, and then what was left only involved derivatives of phi. And that tells you that, just like in string theory, that e to the 2 phi is the loop counting parameter. So the stupid argument is that if you take e to the 2 phi, any loop you calculate will be proportional to e to the 2 phi. But the flux quantization related phi to the radius. So e to the 2 phi in these theories is 1 over the radius to the 4th power. And so any loop contribution to the brane, which is proportional to e to the 2 phi, or in the bulk for that matter, gives you something in the vacuum energy which is the Kaluza-Klein size rather than the brane size. So that's so far, if you do the explicit one loop calculation, the way this happens is really, again, stupidly obvious. If you kind of go to the Einstein frame in 6 dimensions, any mass you would have had in the 6 dimensions becomes proportional to the exponential phi because of the transformation to the Einstein frame. And that just says that the bulk doesn't have anybody who's heavy. All the masses in the extra dimensions are of order 1 over r. And so you integrate them out, it's not a big surprise you're getting things that are order 1 over r. The interesting thing is that the contributions, the things that you worry about would be things which involve the big mass on the brane and the small mass through a bulk loop. And so here, so that's at least a 2-loop thing, and of course we haven't done a 2-loop calculation, but if you do a Gilkey analysis, then, I guess the safest thing to say in this audience is that this argument of that things are proportional to e to the 2 phi is still true. And that although you get the mass dependence that you expected to get, it comes multiplied by factors of e to the 2 phi, which make it anomalously small. So I think this is going to turn out to be an example where the loops are also safe, but the bulk loops are the ones that are the dangerous ones. The remarkable thing is that the brane loops were not a problem. That's the thing that should be the surprise, because the brane is a thing that has no supersymmetry. It's something which didn't deserve to be, loops of those things didn't deserve to be dropping out of the cosmological constant. All right, so what's the bottom line? The bottom line is back reaction beyond codimension 1 is largely virgin territory. And it's virgin territory just because of this matching, the precise statement of the matching story of how near brane boundary conditions or derivatives are being related to brane properties hasn't been worked out in detail. And so I gave you some codimension 2 examples of how things work. The same logic works for codimension 3 and higher. The thing that's a little bit technically harder is that whereas you only saw logarithmic divergences in the codimension 1 case, you see power law divergences in the higher codimension cases, and those are kind of more of a pain to deal with, but they're dealable with in the same kind of logic. Same as renormalization for loops were with power law divergences. So it's kind of a lot of fun playing around in virgin territory, and I think there are surprises in that territory. The existence of exponentially large dimensions, and the hope is that there's the surprises are going to be surprising in an interesting way. That the naturalness issues of low energy physics are going to be addressed in a counterintuitive way, which is counterintuitive because our intuition has been based on physics which either didn't have back reaction or had back reaction in a very limited way. So this vast unexplored territory, we're having a lot of fun. Please join us. From the point of view of string theory, I think what the way to think about what we're doing is you know, the landscape problem, the way I view it, is not that we have to think anthropically. It's just that there's a raft of solutions to string theory, and you're trying to find the one that describes us. And it's hard. So you're looking for modules. You're looking for things that if I build in this module, then I'll get 3 generations, or I'll get chiral fermions, or I'll get this or that. And so we're looking for modules that build in technically natural features. And what we're groping towards here is a set of modules which will give you, hopefully, the cosmological constant problem, but also things like large extra dimensions and ways to address the hierarchy problem. And so it's not known yet how these 6-dimensional theories embed into string theory, because the particular supergravity I'm using, its provenance from 10 dimensions is not known. But I think it's well worth looking for, and so I urge you all to help us look for it. So thank you for your time.
Questions? Sorry, maybe I missed something important that you probably said. If you go just 2 slides back, when you had this the third example.
Yeah.
So what if I now change the brane tension by a certain amount? How does the cosmological constant react? And the brane doesn't, in this case, the brane doesn't couple to phi, right?
Yeah. So classically, it doesn't. The curvature doesn't change at all.
Sure. But what happens at the loop level?
Oh, at the loop level. So if you,
I now change the brane tension by a certain amount, delta t, right?
Mm-hmm.
And I want to see how much the cosmological constant changes, because that's the goodness of your solution to cosmological.
So what will happen is that the tension will be, it used to be something which is independent of phi. Now there'll be some loop contribution coming from the bulk, which will have an e to the 2 phi in front of it. So there'll be no phi dependence here.
Oh, but I see.
And so the thing is, now you can just kind of crank that through what I told you again and ask what happens.
But
and now you get something non-zero.
But you're maintaining that if I add to the brane just by hand a constant piece which does not depend on phi,
yeah, then nothing happens.
Nothing happens.
Right. So if you had a loop that did
you're
not,
still maintaining completely 100% cosmological constant solutions through self-tuning is just realized here. Period. Is that right?
Say it again.
The cosmological constant solutions through self-tuning, is 100% realized here.
I think so, because in the sense of what's going on, the adjustment. The way I understand what that means is that there had to be a field which was adjusting to make things stay zero, and the field that's doing that in this case is the flat direction. So you had a flat direction, and the thing that I didn't emphasize was that the flat direction did not appear in any of the equations of motion, but it appears in the flux quantization condition. And so the obstruction to without the brane localized flux to perturbing the tension was flux localization. And what happens now is that the brane flux has to adjust in a dynamical way to compensate for whatever tension you put in. And the way it can adjust is that it depends on this flat direction. And it's the only thing that depends on this flat direction. So what it does is it's the thing that picks the value of the flat direction. And that's the adjustment, essentially.
So, Cliff, one thing I just want to ask generally, so from a string theory perspective, there's some sense in which you kind of think of dealing with objects, and you say, well, like the D3 brane is the easiest object to deal with, and then as you move up and up, D7s are pretty hard, and then you do F theory, and imagining putting something like a non-supersymmetric D9 or D8 or something is just a really horrible thing. Whereas the way you've kind of presented it, it seems that it's going the other way.
Right.
The codimension 1 objects are easy. Codimension 2 objects, you can do. And something like a codimension 6 object, like a D3 brane, you don't even want to.
Right. But I think it's not inconsistent in the sense that the hard thing would have been from the bottom up, from the top down point of view. The hard thing would have been to predict what the action was. So I'm saying that if I take the action, if you give me the action, then the matching to the bulk is easier to lower the codimension. But it's probably true that it's harder and harder to know what the action is if you actually think you understand the physics of that thing.
And the flat direction is of course crucial in that thing, right?
Yes, definitely.
Massless system, and this flat direction is a truly massless field. Is that right? From the 40,
No, it's not mass.
You'll probably say there's no 4D effective theory of this, right? There just isn't a 4D effective.
That's the question, right? There has to be a 4D effective theory because 6 months ago I would have denied there was a 4D effective theory. There had to be one. But there has to be one because forget the logic that says it didn't have to be one was that the cosmological constant problem is all about ultraviolet physics, which is bigger than the Kaluza-Klein scale, and that's in 6 dimensions. But this classical story I told you was true for any mass. So you could take a very small mass in the brane and integrate it out, and it would give you no contribution to the cosmological constant as an exact classical statement in the bulk. And if the mass is small enough, I can do that in the 4-dimensional theory because I can make it smaller than the Kaluza-Klein scale. So there has to be a 4-dimensional description. And I think we're like 80% to knowing what that is. So there's nothing I can defend in front of the cameras here, but I think there is a picture that's evolving, emerging as to what that description is. But I think you're right that there has to be one, and I think that's the key. The key way to understand this would be to have the 4-dimensional way of phrasing this mechanism.
So, but before I change delta t, before I do anything with the delta t, is the bulk stabilized in that solution? I mean, is the size of the bulk?
So what happens is that the flux stabilizes the radius, and one combination of the radius and the dilaton, and then the branes are stabilizing the other combination. And so in the end of the day, it's all stabilized.
There's no massless field.
Right, but one of them is very, very light. It's going to if you in the story that I'm telling you, if you did a generic expansion of the potential and powers of 1 over r, if it's true that the first term starts with 1 over r to the fourth, which you would need for the cosmological constant problem, the mass that has to be there for that field would be the Hubble scale. So there has to be a very light field in that.
Sorry, I'm confused about the Hubble. I thought we were talking Minkowski. Is this not a Minkowski solution? What do you mean by Hubble's?
No, there's a classical statement and there's a loop statement. So what I was telling you was a loop statement. Once the dust is settled and you calculate everything.
Let's do the classical level. Just the classical level.
Okay. So the classical statement is that there's a flat direction which I can dial and I can lift it by changing the parameters of the brane couplings to fields. And so I can dial the mass in particular. I can make it 0 or I can make it non-zero. But this mechanism that's making so now you're going to ask, so if I choose things in such a way as to lift the flat direction and get a 0 curvature, what's the mass? And it's not 0. But it depends on, it scales with the brane properties. But it's something which is below the Kaluza-Klein scale.
But I don't care, even if it's below the Kaluza-Klein scale, even if it's very, very small. So below that small mass, there's a 4D effective theory.
Right.
With the vanishing cosmological constant. And you know what I'm going to ask next. How do we avoid Weinberg's no-go theorem? Because you have...
Weinberg's no-go, that's the easy part. Actually, Weinberg's no-go theorem, I showed you that was part 1. Weinberg's no-go theorem, so Weinberg's no-go theorem, what does he say? What he says is that the context where he was saying it before was that people said, well, scale invariance is very, very tempting for the cosmological constant problem because if you have scale invariance, you're guaranteed the scale invariant minimum is at 0. But now if you spontaneously break scale invariance, you have a whole flat direction and it's tied, all the scale breaking solutions are tied to the scale invariant solution by a scale transformation. And so they have to all be at 0 because they're anchored by the scale invariant solution. And so that sounds like that's great for the cosmological constant problem. The scale invariance will make you can have scales but still have 0 potential. And then what Weinberg's objection is he says that nothing scale invariant in itself can't forbid a potential which has got only one minimum at the scale invariant point. And that's true. So loops, generically what they do is they lift the flat direction, they give you the thing which is only a scale invariant minimum.
Weinberg's no-go theorem is not about loop. My memory is that it's something much simpler. It's simply that in the effective theory at very, very low energies, below the mass of the lightest field,
right?
You have
to have an exponential potential, basically, is what he says. Because scale invariance forces it on you.
But that means if you have an exponential potential of a field that's part of your theory, then you have unavoidably no mass gap. I mean, this means that the field runs, so there is no...
Right.
So there is no 4D effective theory. That's what so after all...
Well, the 4D theory, but it's just something which has there's no static vacuum because you have things run off to infinity.
I see. And your solution is in that context. So the solution just keeps running, basically.
So the scale invariance gives you what he says you're supposed to get. He doesn't tell you how big A is.
What is your in your model, in the construction, what is this field that keeps running forever?
Same field. So the two things that make... Yeah, basically. So the two things that make Weinberg's theorem not a problem for me, there's two things. One is that it's not scale invariant, right? There's lots of things here that are breaking scale invariance. So it doesn't have to have this shape because I'm going to break scale invariance.
Sorry, Weinberg's theorem is not about scale invariance.
There's also just because there's the Gauss talk at 1:15.
Right, people have to eat.
Which some of us might want to go to. We probably ought to.
So let me finish my answer, which will take 2 seconds, and then we'll be done. So the thing is that Weinberg is saying something about scale invariance. That's what the whole thing was about. And so the two things that he doesn't say is he doesn't say how big A is. And essentially what I'm giving is an example where it's not scale invariant, so you get things that are actually more complicated than this. But the most important point is that the size of A is something which is not constrained by his theorem, his no-go theorem at all. And what I'm showing you is an example of a theory where supersymmetry is making it much smaller than you thought it should be generically, in a way which is not coupled to what you would have thought from particle physics phenomenology for supersymmetry, because on the brane, supersymmetry is badly broken, there's no MSSM, but nonetheless, that's not giving you a big contribution to A. But that still doesn't contradict Weinberg's statement that you had to have this functional form. So that's what we should eat, and I'm sure we'll talk about this more over lunch.
Just to remind, 215, there's a dense colloquium.
So yeah, so there are two talks this afternoon people may want to go to. Neither are directly with the program. So there's Gao's talking at 1:15 here on will computers become mathematicians, and then at 2:15 Ben Allen's talking in Dampt on natural supersymmetry.
That's a colloquium.
That's a colloquium.
What is that?
It would be in I think meeting room 2, which is the main one.
It's the one that's underneath where we have lunch.
Ah, okay.